And part of this talk is going to be recorded. So there's going to be some super secret data that's going to be presented that you all will get to be privileged to watching it live, but will not be posted. So just as an FYI. All right. So, okay, another thing, our website is going to be hopefully revealed Monday, if not Monday, early next week. And no one has given me any images. So please send me things. It's better than it sitting in a folder on your laptop. I know, like, for example, when you choose images for a publication, sometimes there are other ones that are almost as nice and they're just sitting there, like intravital or a pathology and immunohistochemistry, a cell that looked cool. We would love to put it on our website with your name on it. Like I said, better than just sitting on your computer. So please drop me those on Slack and we will feature them. We will also have our social hour right after this at 2 p.m. Kirk is now hosting because Laura has been summoned back to lab. So there is a new link. That link has been updated on the Google Doc and in the Slack channel. So join us there. Everyone's been really, really positive about it. And it's a great way to, relax a little on a Friday. I think that's everything I have to yell at everyone about. Just a preview of next week. We have Katie Catherine, Jorge DePaula, Mike Hollenstadt, Andrew. Oh man, we had a switch. I also really appreciate people switching. Andrew Volk, chromatin assembly and normal hematopoiesis. So that's going to be great on Thursday. And then Tim Stalker on Friday. Cool. All right. So with no further ado, I'm really interested in coagulation in dirt. So please, let's get going with the science.
Okay, sounds good. Yes, Kelly. Yeah, thank you very much for letting me sign up and letting me present, and thank you very much for keeping our community connected and expanding our communities. Thank you. Okay, so today I'll tell you about two different projects. So one of them is about a natural modulator of hemostasis, or what I believe to be a natural modulator of hemostasis, that being dirt. Another one is novel modulators of hemostasis and thrombosis related to RNA gene therapy. And so yes, I'm in at the University of British Columbia in Vancouver in the Michael Smith Laboratories and Department of Biochemistry and Molecular Biology. So okay, yeah, so here's one picture of UBC. The reason why I want to show you this this nice picture of campus and the ocean and the mountains is we are recruiting a postdoctoral fellow in molecular biology and platelets. So UBC is a wonderful place to grow a career, to live, and to do excellent research. And so yeah, it's really close to world-class city of Vancouver, so it's just a 15-minute drive there. Okay, so to start, I want to tell you the first story about I believe to be a natural modulator of hemostasis. And so the question that we're asking here is, what is the physiological role of coagulation factor 12? And so as this groundhog is thinking and wondering about this, I wanted to point out, where this groundhog lives. It lives in the ground. So it's surrounded by all of this soil and silicates. And so I'll come back to this. The second story I'll tell you about are novel modulators of hemostasis and thrombosis. And so we have a growing library of RNA that for use in vivo in animals that are available to collaborators and friends, such as all of you that are tuned in today. And yeah, thank you all for tuning in. And so yeah, currently available so I'll go into details on some of these in the second part. And so we have siRNA to decrease the plasma concentration of factor 13. We also have one for fibrinogen, TAFI, plasminogen, and mRNA for for a couple different proteins, including factor 7. And so we're generating a library of agents, gene therapy-based agents to decrease the expression of coagulation protein, especially those involved in fibrinolysis. And so if there's any you would like, I hope you'll let me know, any of these or any other targets. And so I'll talk about 13 and fibrinogen and a little bit of fibrinogen later on, as well as mRNA for platelets. I won't be able to discuss these other targets today. Before we do that, though, yes, I want to tell you a story. We think that coagulation factor 12 does contribute to hemostasis, which might be different than what many of us thought for a long time. It's particularly the case when activated by soil and wounds. And so Li Jianjuang, a graduate student in the lab, has led this work with help from many other people. The collaborators are David Galani at Vanderbilt, Les Lab Coolidge in soil science at UBC, and Martin Luna in the Vancouver Aquarium. So this might be the, I'm guessing this is the only blood-bone talk where we've had the collaborators are hematologist, soil scientist, and a marine veterinarian. So I think we're in for a fun story. I hope you have fun with me hearing about this. Okay, so the question we're trying to address is, I think, perhaps the oldest unanswered question in hemostasis biochemistry, which is, what is the physiological role of coagulation factor 12? And so, yeah, a hero of mine, Earl Davey, as well as Ratnoff, in one of the first papers on blood clotting and the cascade of reactions, this one in Science in 1964, they described the intrinsic pathway leading to the formation of fibrin from the activation of a coagulation factor 12. And there was a question mark here. They weren't sure what the in vivo stimulus for factor 12 was. And so it was a question then, and it still remains a question. And so, yeah, as most people on the call know, probably everybody, clotting can be driven by two different pathways in vitro. And so if you have blood plasma or blood and you add tissue factor to it, the factor 7 will bind to the tissue factor to lead us down through a series of enzymatic reactions that lead to the activation of platelets that are not shown here, as well as the cleavage of fibrinogen into fibrin to form the cell-rich fibrin clot. The other pathway, sometimes called the intrinsic pathway, involves factor 12 and the activation of factor 12 to 12A. Also part of the contact activation. And contact activation, contact may come because in many cases this is activated by when it comes in contact with surfaces. And so in vitro, there's a number of surfaces that will activate 12. So clay is a great activator of factor 12. So factor 12, it binds to these surfaces, can get auto-activated. 12A can activate more 12, as well as activation by other enzymes. And so clay is a good activator. Silica is a very nice activator, as is mica. Ellagic acid, small molecule from plants, is an activator, as well as others like polyphosphate, some nucleic acids, amyloid peptides. And so these are used for sometimes they're used for various applications. So clay is used by humans to stop severe hemorrhage. So it's used on gauze. So all American and Canadian combat soldiers carry combat gauze or quick clot combat gauze that is loaded with clay to stop severe bleeds. Silica and ellagic acid are used in clinical assays to measure clotting. So there's always been, for a long time, there's been a question, what is the in vivo activator of factor 12? So some of these down here likely play a role in thrombosis, but it hasn't been clear what the activator is that if any, plays a role in helping to stop bleeds. And there's reasons to think that there is no activator for factor 12 to stop bleeding inside of our bodies. And so people that are missing factor 12, they don't seem to have a They don't seem to bleed excessively. And this has been well established for a long time. Mice that are missing factor 12 don't seem to bleed excessively. And there's also a strangely large concentration of factor 12 and poor kinetics of factor 12 compared to the other coagulation factors. That suggests you need a huge amount of activator, and we just don't know what this activator in vivo for hemostasis could be. And so there's a couple questions that come out of this. So one that I just asked, so what is the physiological role of coagulation factor 12, particularly in hemostasis? And maybe the answer is none. Also a question, why does clay, an artificial surface, why does it stop bleeding? And really, besides using it as a hemostatic agent on gauze, maybe the answer, really, who cares? is one potential answer to this. Okay, so regarding clay, I wanted to give just a couple reminders of what clay does. So I want to remind you that terrestrial mammals, like humans, are often covered in soil silicates. And so this is another picture of the UBC campus. We're building lots of buildings, and I think UBC will weather the pandemic okay, continue to be able to build buildings. But what I really wanted to point out here is that as humans, and you can see that they are covered with a thin layer of soil. And so soil contains mostly silicates. And silicates are a main component of the Earth's crust. So besides water, they are the most abundant component. As I mentioned earlier in the presentation, some terrestrial mammals even live in the dirt. And humans, I think our ancestors were much greater contact with dirt. So before shoes were invented and before we had wood or carpet floors, we were in a lot more contact with dirt. All right, so we wanted to test this. Is soil an activator of factor 12? Which we hope would shed some light on this question. Is soil the activator of factor 12? So I want to ask if it contributes to hemostasis, and what I'll show you is that yes, we think factor 12 does contribute to hemostasis, particularly when wounds contain soil. And so we did this study here, blocking out part of the data for now. And what we saw is similar to what people had seen before. And so we're comparing normal wild type mice to factor 12 knockout mice. And so what we see, if we do a transection of the tail in this bleeding model, and we compare the wild type to the 12, we don't see a difference in blood loss. So the factor 12 don't bleed more than the wild type in this condition, in this very clean setting. If you had tissue factor in the end of the tail, that helps stop the bleed immediately, as is expected. So this is consistent with what had been seen for a long time. No difference in bleeding in these factor 12 knockout mice. However, the story is a little different if you put soil on the tail of the mouse. And so if you put soil on the tail of the mouse, it stops bleeding immediately, except if the mouse is missing factor 12. If the mouse is missing factor 12, there is blood loss associated with this. The soil doesn't have an effect when the mice are missing factor 12. And so does factor 12 contribute to hemostasis? This data suggests that it does, but wounds need soil in them. Okay, so here's just some more data showing that with with another soil. These are soils that are Canadian standard soils used by soil scientists. Later on in the presentation, I'll show you, we started to use a variety of soils that we've all collected ourselves from various places. And so in this study, enhancing the bleeding, making this bleed a little more severe just by administering aspirin. The only reason we administered aspirin or ASA was just to have more bleeding. And so we see the soils are still able to stop this, as well as clay K. This is a kaolinite. Kaolin is what is on combat gauze. And so you stop these bleeds readily in these wild type mice. Titanium is a weak activator of clotting. So weak activator of factor 12, excuse me, very weak activator, but it does have decrease bleeding, perhaps a small amount, but it's not as great as these. This is really a control to look and make sure that this wasn't a mechanical effect. It wasn't just that we were stuffing the wound or placing these materials on the wound, and it was a mechanical effect that led to it. And so it really looks like it's the soil and the soil components that are clotting. In the factor 12 knockout mice, they don't, even on the aspirin, they don't respond to these services. They still clot really well by tissue factor. Okay, so we did a number of studies just to look to make sure that it really was factor 12 that was getting activated, and not and to test if to test which components of the soil, and to look more to verify. I'm not showing all the data, but to verify that it was factor 12 activation with an activated 11, and that that it interacted with prekallikrein in the way that we expected. I'm not going to show all the data, but this is just in vitro. This is human blood plasma. And in this case, looking at the turbidity of clots, the fibrin clot formation, and in this case, looking at thrombin generation with a fluorescent substrate. We see the same thing in these two graphs. So in normal plasma, these soils clot blood faster, but if we deplete the factor 12, or if we inhibit factor 12 with corn trypsin inhibitor, there is a long clot time, and so the soils do not clot this blood fast if factor 12 is immunodepleted from the plasma, or if we inhibit it with CTI. Okay, so we are wondering, what's in the soil that that does it? Is it the clay particles in the soil? Yeah, it seems to be the clay. And so what we did in this study is we separated the soil into high clay and low clay fractions, and looked at the rate of cleavage of a substrate by 12A. And so in this case, we used purified 12. We added it into solutions containing these silicate materials. What we found is that if we took intact soil, that's what I showed before. This leads to the formation of 12A. If we separate it into high and low clay, what we find is that what we find is that the high clay has the greatest cleavage of the substrate. So the high clay has great cleavage of substrate. The low clay fraction does not. So this has a low activity in being able to convert 12 to 12A. It could be that it's not the clay that's in here, but it could be that it's organic matter, particularly endotoxin and lipopolysaccharide LPS. So first, so we did a couple things. We sterilized the soil just to make sure there's no living microbes in it. We also did another treatment with sodium pyrophosphate to deplete the organic matter in it. And we didn't see any changes in the fibrin clot formation, the turbidity test. And so what this means is that it didn't, in this initial crude experiment, it didn't seem to be, you didn't need live microbes and didn't need large amounts of organic matter. We further looked to make sure that it wasn't endotoxin or LPS that was leading to this effect. And so we flame heated the soil for an hour. And when we did that, we decreased the endotoxin level. We even did this with compost. Really healthy compost that we use in the garden. And so, it depleted the endotoxin by burning it. And so what we did in this study is then we looked to see if flame treating these materials changed their ability to clot, and it didn't. So when we burned off, eliminated a lot of endotoxin, it didn't change clotting. And so this is all supporting that it's the clay in the soil that's doing this. Wanted to point out, in this study here, the sand was removed. So the soil has a lot of clay. Normal soil would have a lot of clay, sand, and organic matter. So it's really the clay, not the sand. I was surprised by that, but the sand is not a great activator. Probably because those particles are bigger, maybe because the surface of the sand is different than in the silica that's used in clinical assays. So we wanted to know, I wanted to understand other properties of these materials, of this clay. And so it's negatively charged surfaces usually that will initiate this pathway, help activate 12 to 12A. But it's interesting, we only saw a moderate correlation with the size of the zeta potential. And so all these materials are negatively charged. They have a negative zeta potential. But the ones that had the biggest negative charge, the most negative zeta potential, there was a moderate correlation of their ability to clot fast. but it's only moderate. Although there is a really strong correlation, which is the surface concentration of silicon. And so using a mass spec technique, time of flight secondary ionization mass spectrometry, we found that there's a strong correlation with the surface concentration of silicon. And so, yeah, so we hear that negatively charged surfaces will activate factor 12. It might actually be that high concentrations of silicon on the surface are what activate factor 12. We also found a moderate correlation with the concentration of iron and zinc, but not a few other metals that we tested. And this is in line with the literature. Interestingly, yeah, so the activation of 12 leads to, can lead down through to clotting. It can also has other effects. And so one thing that it can do is it can lead to the cleavage of high molecular weight kininogen. And that's what we saw when we added soil to plasma. So this is just looking at the Western blot, looking at the full length of high molecular weight kininogen. And so when we allow the soil is able to make active 12A, and it's not inhibited, and we let the plasma clot with the soil in it. What we see is that high molecular weight kininogen is cleaved to its smaller fragments. And so this is interesting because the cleavage of HK, high molecular weight kininogen, this leads to the formation of bradykinin as well as antimicrobial peptides. In addition, the enzyme that's doing this, the kallikrein, which is activated from prekallikrein by 12A, it also activates parts of the complement system. And so what this is suggesting, this is we have not verified this yet, but what this is suggesting is that soil activated 12, in addition to triggering clotting, might also contribute to host defense and innate immunity. And one way to rationalize this is, okay, you have a whole bunch of mud, dirt, bad, in your wound, lots of microbes there. What we think might be happening is 12 gets activated. It helps trigger the formation of kallikrein and cleavage products of HK, which can help rapidly kill as much of those microbes that are now in the wound as possible. So 12 is sensing that soil to help clot the injury, as well as help fight the antimicrobial, help fight those microbes. And so we haven't verified this host defense process, but it's something I'm interested in working on and collaborating on if anyone's interested. So if you happen to know about the evolution of the contact system and factor 12, remember that things are different in some mammals. And you all know that not all mammals live in the dirt. And so, yeah, so our silicates, question is, so for Helen and Chester here, are silicates part of their coagulation system? And so Helen is a Pacific white-sided dolphin, Chester is a false killer whale. These were at the Vancouver Aquarium. I think Helen might still be there. And yeah, so they're not in contact with dirt, so our silicates part of their coagulation system. And so, yeah, so Doolittle did a lot, and colleagues did lots of studies to look at the evolution of blood coagulation. And so they looked really hard at factor 12. This is an area where David Galani has contributed major to also. And so if we look at the evolution of clotting, factor 12 appeared between fish and amphibians and terrestrial vertebrates. So it seems as fish transitioned to the land, that's when factor 12 showed up. Factor 12 actually has been lost in some terrestrial vertebrates. And so birds have lost factor 12. Speculate it's because they're not on the ground as much. Of course, chickens, they're on the ground, but for most case, birds are not on the ground as much as, say, lizards. And cetaceans, so what the dolphins, whales, and porpoises, they actually have a factor 12 pseudogene that's incapable of protein expression. And so, yeah, so vertebrates that are not in contact with soil seem to have lost factor 12. And so we might speculate that humans might someday lose factor 12 if this is indeed the main mechanism for what its function is. So I wanted to test this. Oops, sorry. I wanted to test if soil triggers clotting in the blood of cetaceans and birds, and it does not. And so in orange is human plasma, which clots really well. from these soils and clay. But if you look at, we collected plasma from dolphins and we got plasma from chicken, and the silicates don't touch this. So tissue factor, human tissue factor or not human tissue factor, but tissue factor will clot this, but these materials won't. Okay, so almost done telling you about soil and its role in hemostasis. But some people might ask, would I use soil for controlling severe hemorrhage? So I have to say no. Do not recommend that you rub dirt on your wound. I can't recommend this at all. And for myself, I think about myself or my family. Here's a picture of your daughter. Yeah, would we use soil? So I would say only in the I can't recommend it for you. For me, only in the most remote settings. There's really absolutely no options. Yes, there's a high chance of infection here. And ideally, that soil is flame treated. So you'd have some on hand that's burnt, put over the fire to really make sure that it was sterile. But I can't recommend this at all. But I don't know, it's interesting. I'm not sure, when we're doing landscaping, I'm not sure if my daughter here, I thought she was just playing in the dirt, but it looks like she might be collecting some to maybe put over the fire and sterilize in case her dad injures himself in landscaping. Okay, and it's nice they're actually back at school yesterday. Two daughters in primary school. Okay, so so if this sounds crude, maybe the slide that convince you otherwise. So we may not be on Earth together. In the best case scenario, we can be on Earth for a few billion years. Eventually, we won't be able to be on Earth. The sun will expand. So what do we want to do about this? And so one question we have is, can extraterrestrial soils trigger the coagulation cascade? Can the surface of a Mars or Moon, they actually have a high concentration of silicates? And so we think we can, and that's something that we're testing. Okay, so that was the story that I wanted to tell you about how we think that factor 12 is a part of does play a role in hemostasis, as well as soil. And so in addition to the coagulation factors that we know and love, there's also, I think, soil factor. Okay, so let's switch gears a bit. And Kelly, this is a cue that we talked about before.